mass profiles of early type galaxies. Thank you.
Okay, I'd like to start by thanking the organizers for letting me give Aaron Romanowski's talk this morning, and Aaron's going to be giving Gene Brody's talk this afternoon. So I'm going to talk about mass profiles and early type galaxies from cores to halo, in particular what the Slug survey has to say about this. So starting off with some motivation of why we want to look into the outer parts of early type galaxies. This is a plot of fractions of various quantities against the effective radius. So the profile that you're probably familiar with is the stellar mass or the luminosity profile, and by definition when we're at one effective radius, the half-light radius, we're at 50% of the stellar mass. Here's a curve for angular momentum, J, so if you're interested in kinematics, that would be the curve for you. And down the bottom here is how the total mass profile would go with radius in an early type galaxy. So you can see when we probe just into one effective radius, which is often the case with spectroscopy, that we're only sampling 50% of the stellar mass, 10% of the angular momentum, about 5% of the total mass. You want to be out much further in radius. So the Slug survey is probing with stars around 2 to 3 effective radii, and with globular clusters out about 8 or 10. So one effective radius is only half or even less the story. Another reason you'd like to go to the outer parts of galaxies is the assembly history is preserved in those regions because the dynamical times are long. Here's a figure of merit for integral field spectroscopy surveys. Well, it was made a few years ago, with the years corresponding to when these surveys should have finished collecting data. Just about most cases it took longer than expected. SAMI survey only just finished a few months ago, and Slugs took till 2017, all because of weather. All right, so what I'm showing here is the velocity resolution of the survey against, again, how far out they probe in early type galaxies. So ideally you want to be in the top right-hand side of this diagram, large radii but with very good velocity resolution. Each symbol of each survey is coded by the size, the number of galaxies in each survey. Probably corresponds to the number of people working on that survey. A pioneering one, of course, that probably many of you are familiar with is the Atlas 3D survey, which has given us lots of information about early type galaxies. Number of surveys that are still producing results, including MANGA coming out here at Santa Cruz. So the Slug survey with its stars has very good resolution and probes out to about 2 or 3 effective radii, as I said. And then we've got this X factor of globular clusters out at radii of about 8 or 10. So Slugs, the imaging comes from the Super-U telescopes, telescope, singular, and spectroscopy comes from Keck 2. Team members, it's just a small team, and it's mostly here at UC Santa Cruz and also at Swinburne. But I'd like to acknowledge the work of all the students and the postdocs who are largely producing the papers on this survey. So here it is quickly. Here's our website. So it's a small survey of only 25 early type galaxies drawn from the K-band luminosity function. And they cover this mass range of log space of stellar mass of 10 to the 10 to 11.5. Okay, so all of their inner regions have been probed by the Atlas 3D survey, and we use Slugs to probe further out to larger radii. They're all pretty nearby, within 30 megaparsecs, so they all have NGC names. They're all pretty familiar to those who work on nearby galaxies. There's a range of environments, field group through cluster, but again, it's only 25 galaxies, so it's hard to probe for environmental effects. A bunch of papers to date. You can go to the website, and our general aim is just to understand early type galaxy formation. So here's what they look like, just a pretty standard set of 25 early type galaxies. So here's one of our images from the Super-U telescope. It shows a galaxy in GC 4365. Here's 10 effective radii of that galaxy. And the globular clusters that we've selected just from the photometry alone are shown by little white circles here. So you can see that this galaxy has about 7,000 globular clusters. So this is one of the reasons for studying nearby early type galaxies instead of, say, the Milky Way, which has maybe 200. We've got 7,000 to work with here. The other part of the survey, of course, is Keck Deimos spectroscopy. We work at the calcium triplet lines, have a resolution, which will be little sigma of around 23 kilometers a second. So we're getting spectra of both globular clusters in that sort of effective radius range, about 2 to 10. So we get their radial velocities and we get their metallicities. But we also get galaxy starlight in the same mask in that sort of range of 1 to 3 effective radii. And from that, we can get 2D maps of velocity, velocity dispersion, the higher order moments, and metallicity. So here's what we actually do with Deimos. Deimos, of course, is a multi-object spectrograph. So we take the spectrograph and we sort of spin it around in this pinwheel pattern to build up a good azimuthal coverage of the galaxy that we're looking at. So the slits at the center of the galaxy, we focus on getting starlight, and the ones in the outer parts, we stick on globular clusters and get that at the same time. So here's just an example of some of the velocity maps that we've created from the starlight. It's a bunch of our galaxies. You can see some nice rotation. So what we give up, I suppose, if you like, is we don't have the high-density spatial sampling that, say, Atlas 3D does with an integral field unit in the center, but we've got slits out at larger radii, which we sample the velocity field in this case, and then make these two-dimensional interpolated maps. So I want to show you just one example of the kinematics that you can get with this approach. So this is going back to 2001. This is this Galaxy NGC 4365, and this is what it looked like with an IFU back in 2001. And you can see that it's got a core that rotates this way, and further out there's a hint that the rotation is doing something different in this galaxy. It's actually a decoupled core. So here's the Slug's view, and so those of you at the back, you may not be able to see this, but that's the whole point. So that's that little core doing that in the Slug's view, and now we can see that indeed most of the galaxy is rotating along this axis, which is not along the major axis. So if you like to think about it, this galaxy is rolling rather than rotating. So as I mentioned, of course, we've got globular clusters, and we use that as well to probe our galaxies. This is just one slide summarizing the globular cluster situation. So it shows the velocity of each globular cluster minus the systemic velocity of its host galaxy, divided by velocity dispersion as a function of effective radius again. So you can see all of our over 4,000 globular clusters here as little dots. And you can see that we sample quite well out to about 10 effective radii, sometimes even 20 or 25 effective radii. We find globular clusters associated with the host galaxy. So they're great probes of the halos of these early type galaxies. So on to some results now. So here I'm showing what's called gamma tot. It's the slope of the total mass density profile. Now the reason we were interested in this is because it, from simulations, should tell us something about the accretion fraction. So in the two-phase picture of galaxy formation, you've got some in situ formed stars and some ex situ or accreted stars. We as observers like to get a handle on what's that accretion fraction. And it seemed from simulations that a proxy for that was this total mass density slope gamma tot. So that's what I'm showing here against stellar mass. The Slug's galaxies are these sort of brown symbols. This was work done by my PhD student, Sabine Velstedt. One of the things we've managed to do actually is to go out to 4 effective radii to measure this total mass density slope. Other people have done this work, say, with strong lensing. You tend to do that at the Einstein radius, which is usually less than 1 effective radius. So it's really nice to be able to probe out so far. So, and we're comparing our data points with a couple of simulations. So the black symbols here are the Magneticum hydro simulations, and then the small blue symbols are the Eagles simulation of centrals, and there's some Eagle simulations of high resolution recalibration, which don't seem to be much higher than the other 2 simulations. So I would say our data is perhaps closer to that of the Magneticum simulations, but we're not inconsistent with Eagles. There's not that much difference between the 2 simulations. Just to sort of take a step back now and tell you about how we got that mass density profile, we start with the data from Atlas and Slugs. We make these kinematic maps. We do a model of the galaxy using jam modeling, then measure the slope of the total mass density profile as a function of radius. So here's slopes of our various galaxies. It shows you some exponents of the slope here. Basically measure that slope in one dimension, and that gives us the gamma tot. That's the slope of the total mass density profile, which I'm plotting on that y-axis there. So some agreement, perhaps some tension with the simulations there. Another result from another PhD student of mine at Swinburne, Busola Alabi, who's now a postdoc here. So in this case, Busola used the motions of the globular clusters around these early type galaxies to infer the total dynamical mass, enclosed mass within that radius. And that radius was 5 effective radii. Take away the stellar mass, and when we look at the dark matter fraction. So these giant yellow symbols are the Slug's galaxies, and that's their dark matter fraction within 5 effective radii. So we're going out much further than people have done before for these types of galaxies. Plotting it as a function of stellar mass, and again comparing it with some various simulations. So what we've got up the top here in this grey line is the illustrious T and G simulations. We've got magneticum again, these open diamonds, that's Remus work here. Both of these simulations, hydro simulations, include AGN feedback, of course. These open squares are simulations from Wu, which do not include AGN feedback. And then there's a couple of models from Jacinto, a couple of galaxies with cold dark matter and the same galaxies with self-interacting dark matter, and you can see the effects that that has on the dark matter fraction in this plot. So our data, some of it certainly is consistent with the latest hydro simulations, but we also find a bunch of galaxies that get down to dark matter fractions that are further below or lower than the scatter seen in the simulations at this sort of stellar mass. Although they might match the Wu simulations, as I said, we know there's no AGN feedback in these simulations. One way to perhaps lower the dark matter fractions, as I said, is to go from cold dark matter to self-interacting dark matter. So I think there's still lots of interesting things to learn in this particular space. This is work now from a PhD student at Santa Cruz, Asher Washerman. You might have heard him talk yesterday about DF2. He's also done some mass modeling of one of the Slug's galaxies, NGC 1407. So he's applied his genes model to 3 different traces that we have. We have the blue globular clusters, the red globular clusters, which you could think of as metal poor and metal rich, and then also the stars. So they all have their own kinematic profiles and density tracing profiles. Another thing that he throws in for the first time is allowing for a radially varying initial mass function. That information comes from the literature using spectroscopy of the stellar populations. So we know that there's some evidence for a bottom-heavy IMF in the center of this galaxy. So he folds that in as well, does his modeling, and finds an inner dark matter profile to be cuspy in this particular galaxy. There's the cusp value there. Here is his radial dark matter profile. So this Asher's work is shown by the green line here in comparison with some other previous works. Potter, Alison Deason, SUV, which is the X-ray measurement. And here is Busola Alabi's 5 effective radii measurement from our globular cluster only work in a very simple approach, which seems quite consistent with this more sophisticated approach that Asher did. He's made this plot that compares this inner dark matter density slope as a function of halo mass across a wide range of galaxies. There's a little schematic of what we might expect from theory in this, although I guess we've certainly got simulations now that suggests there should be cores and dwarfs. He's collected observations from the literature, the green points here, and also just noted, of course, that in this particular mass range where we have giant elliptical galaxies, there wasn't any data or any measurements of this inner dark matter density slope. And here's his cusp value for NGC 1407 placed onto this diagram. One thing you can also do with the globular clusters from this approach is get an indication of their orbits. So here we're showing the anisotropy of the beta parameter of the blue globular clusters against the parameter for the red globular clusters, where radial orbits would be positive, tangential orbits would be negative. And there's a couple of other galaxies shown on this plot here. So here is NGC 1407, very tangential, M87 here, and NGC 5846. Interesting thing about this diagram is that we would generally expect globular clusters to be on radial orbits, and so we'd be up here in this diagram. So clearly there's only 3 points here, a lot more work to be done, but interesting tension, if you like, with theory of the early stages. Last couple of slides I want to show is about the galaxy halo versus globular cluster mass relation. So many years ago, I found this relatively tight linear relation between the galaxy halo mass, and this just comes from weak lensing, and globular cluster system masses, just adding up all the mass in all the globular clusters in these galaxies and putting them on this correlation here. So we found a pretty tight linear correlation that started to break down here when weak lensing stopped us from measuring the halo mass. So I've gone back to this issue and going back many years later, switched the axes around. So now halo mass is on the lower axis here, and here's globular cluster system mass. That solid line there is the line from the previous plot, and I've simply just extrapolated that linear relation down here. It's not a fit. So here are the data points in the cyan and in brown. They are dwarf galaxies in the local group or the local volume, where we've managed to find globular clusters and added up their globular cluster mass to give a total system mass. The halo mass comes from the kinematics of these galaxies. So here we've got central velocity dispersions for the early types, or Vmax, or the rotation curve maximum for the late type galaxies, and then assuming an NFW type halo, calculated a total halo mass. There's a recent prediction here, semi-analytic model from El-Badri, which starts to decline at the lower masses, which seems now inconsistent with very new measurements of the globular cluster system mass at these lowest masses. And just because it's topical, these red points show 3 UGGs, where these 2 points are 2 different halo masses for DF2 that Asher spoke about yesterday. So one essentially having, the halo having no dark matter being essentially all stars, and then the upper limit that they have on that, and then a galaxy, a UDG in Virgo, and another one in the Coma cluster. How do they get the halo mass of the UDGs? They generally come from globular clusters, globular cluster motions. So they all have a significant number of globular clusters. In some cases, they also have central velocity dispersions. In the cases where they do, the halo masses agree. Yes, that's right. There's an extrapolation, indeed. And there's an extrapolation with all these points as well. But again, it assumes an NFW profile. So considerable scatter, but to first order, it seems consistent with an extrapolation of that linear relation at the even higher masses. So this relation exists over many orders of magnitude, going all the way up to 10 to the 14. Yeah, I've avoided those. Good point. Thank you. These are galaxies without globular clusters. So it's just trying to give you an indication of where galaxies do not have globular clusters start to kick in, if you like. So one way of thinking about this, that these two relations are instantaneous relations, if you like. They show the situation now. If we wanted to look at a mean globular cluster system halo mass relation, I'd have to take into account these galaxies without globular clusters. And for those of you, of course, that are more interested in galaxies, it's at some point, dark galaxies, galaxies without stars, are going to start to be of interest in this kind of diagram, as we've heard about this morning. So in conclusion, Slug survey, it's a chemodynamical survey. We probe stars and our early type galaxies out to about 3 effective radii and globular clusters out to about 10. And the things I've shown you today, I've looked at globular cluster orbits, globular cluster system masses, dark matter fractions, and mass density profiles are all something that we can compare with simulations. And at the moment, there are perhaps some tensions or interesting challenges to look further at. Thank you.
Lots of questions. Yeah, there.
Thank you. Yes, I didn't mention those. So the symbol sizes are inversely correlated with the errors. Very important, thank you. So these guys have huge errors on them, and these guys have very small errors. Thanks for that, I should have mentioned that.
There.
I was very intrigued by the results where you compare the halo mass to the mass in globular clusters. It's been obviously striking that those things trap each other so well.
Yeah.
Do you have anywhere where you can compare where you also show the mass in the galaxy itself, and stars in the galaxy itself? Because it seems like as you go to very low mass, you might end up with almost all the mass in globular clusters, or the ratio of mass in globular clusters to the mass in stars in a galaxy would start to trend toward a very high value.
Yeah, thanks. Good question. So the paper does have a plot exactly the way you're describing it. There's actually, even for these dwarf galaxies, a huge range in the mass that's in the globular cluster system versus the total stellar mass, and that varies from over a factor of about 1,000, from about 0.1% to 10%. So some of these galaxies have as much as 10% of their stellar mass in globular clusters, and that would include the ultra-diffuse galaxies that I showed. They're at the very high end of that distribution.
Yeah, one might just imagine if you go to very, very small systems, or even early in the universe, you might be dominated by star clusters.
Indeed, some people have speculated that it might be 100% in the sense you have a dark galaxy with no stars, but it has a globular cluster.
Joel.
Going back to the slide you showed a moment ago, can you explain what the main sources of error are? And in particular, as you mentioned, the beta parameter that measures the velocity. That's often something that you have to make assumptions about, and that should have a big effect on the dark matter fraction. If it's very radial and you're measuring far out, you're going to see very little velocity dispersion, yet there could be a great deal of dark matter. So what are as you said, the small circles are the ones with the biggest uncertainties, and those are also the most discrepant from the simulations. Right. But for all of them, what are the main sources of error, and is there some way to decrease that error?
Okay, so this plot, we've measured the total mass using the tracer mass estimator. So it's a relatively simple way of just taking the motions of the globular clusters, all of them. No, sorry, yeah. So I've showed a couple of different things. That's why it's been a little bit confusing. So the genes modeling, the sophisticated modeling, has been done by Asher, and I think he's still in the audience. He's raising his hand at the back. He can talk about the beta parameter that he derives from the gene's mass. This particular one, using the tracer mass estimator, just assumes isotropic orbits. Okay? Absolutely, it may indeed not be valid. So we've tried to put in some mild radial orbits and mild tangential orbits into that analysis. It doesn't make much difference to the dark matter fractions that we get out, but those were mild variations. We also have to assume that this is pressure supported, that the rotation's not very large. I mean, we measure rotation and try to make a correction for it. You assume that there's no substructure. Again, we try to measure the substructure in the system to look for dynamical equilibrium. We didn't see much evidence of substructure. So you're absolutely right. There's a whole bunch of assumptions that have gone in there that we've tried our best to test. And then, of course, there's Ash's much more sophisticated modeling, and we can talk to him about that later.
Just a comment. To my knowledge, no one has actually done what really should be done to make the comparison, which is to do simulations with globular clusters, or at least globular cluster analogs, and then measure the globular cluster velocities and so forth, just the way you're doing, and then you can do an apple-to-apple comparison. But as far as I know, no one has done that.
That's right. That'd be great. Excellent.
Okay. I think we should move on. Yeah. Let's thank Duncan again.